Attendees are in listen-only mode.
Good afternoon, everyone. This is Jennifer Beliveau, Director of Sales from Applied Math Modeling and today's moderator. Thank you for joining us online today. We're excited to share with you another outstanding case study using CoolSim software, modernizing existing data centers. With me today is Paul Bemis and Liz Marshall, Applied Math Modeling's President and CEO and Director of Support and Consulting Services, and Todd Boucher, Principal of Leading Edge Design Group. Before we get started, we'd like to inform you that we will have a question and answer session at the end of today's presentation. You may enter your questions in the question panel located on the right-hand side of your screen throughout the presentation. If you're having any technical difficulties, please click on the right-hand of the raised hand icon, and we'll respond to you throughout the chat window. Without further delay, let's get started. Paul?
Thank you, Jennifer, and thanks everyone for attending today. We have a pretty exciting webinar, I believe, that we've put together with one of our partners, Leading Edge Design, and we're going to jump right into that. However, the first thing I'm going to do, for those of you who don't know who we are, we're Applied Math Modeling. We were founded in 2008. We are an outgrowth of the Ansys and Fluent Corporation, where all of us worked and did a lot of work in fluid dynamics and stress analysis and essentially engineering simulation. We have our own company. We still partner with them. We do use their technology, their meshing, solvers, post-processing, but we are responsible for the development, sales, and support of CoolSim, which is an application designed to be used to optimize the data centers. And it is a SaaS-based delivery model, so with CoolSim you pay for what you use in the sense that if you're a periodic user, your cost is lower than if you're a heavy user. We have a subscription model that works quite well, and the tool has been used for both design optimization from a design build point of view and also as an operational tool for just understanding what happens when you move perf tiles around in your own data center. So the tool has turned out to be quite good. We are CFD people, not necessarily data center design people. However, I think we've gotten a lot better at data center design lately than maybe I give ourselves credit for. And with me today is Todd Boucher from Leading Edge Design Group. And Todd, I'll let you use this slide to describe your organization.
Thank you, Paul, and thank you everyone for joining us online today. Again, my name is Todd Boucher. I'm the principal at Leading Edge Design. We're a data center design and consulting firm based here in the United States and with an office in South Africa as well. And we're a firm, we believe data center is a unique environment and with sort of cross-functional needs, engineering, technology, architecture, efficiency. And so our team is sort of uniquely equipped and built to support that diverse ecosystem that we see in data centers. And so we offer comprehensive data center services, everything from the assessment and planning side through obviously design, energy efficiency analysis, and then construction administration and commissioning as well.
Now, the first time I met you, Todd, we were working together on a project over the University of New Hampshire.
We were.
Yes. Okay. So today we're going to take a look at a data center that you worked on recently, and we worked on it with you. Liz did the modeling. Liz is here today to support us in this discussion. Can you give us a brief overview here in this slide of the environment that you faced as you walked in?
Yeah, I'd be happy to, Paul. Thank you. So the organization that we worked with, they're a global telecommunications services organization, and the data center that we worked with is located in the United States, and it's a kind of global operation center for them. It supports both internal operations and processes as well as customer systems. So, with any design, first we obviously want to take the time to understand the business requirements and the objectives, and in this case, as they've evolved to have more of a managed services model, they had a lot of increased uptime and reliability requirements to support 24/7 call centers that their customers have. So important global operations center for the organization. Infrastructure-wise, I think it's pretty typical design that we would consider a sort of legacy data center from a design perspective, and that was about an 18-inch raised floor about 5,000 square feet of white space, 90 or so server racks, and over the years they had grown to 3 individual UPS systems to maintain their N+1 configuration. In addition to that, the cooling mechanism and strategy was perimeter crack units, and there were quantity 5 of those crack units that were designed with the intention of providing N+1 redundancy. And again, just from a global operations perspective, we'll talk some more about the challenges, obviously, that we saw in the data center, but they had some significant IT projects, specifically some virtualization efforts, that were pending and being delayed because of some of the problems that we saw and they were experiencing in the data center. So that's essentially the existing conditions as we found it when we started the project.
So not unusual in terms of what you find. Let me ask you, it's 18-inch floor. That always makes me immediately a little bit hesitant. What was going on under that floor, Todd?
Yeah, pretty typical, as you can probably imagine, in the sense that there were generations of cabling, both telecommunications and power. So all the power distribution was supplied underfloor through floor mount PDUs that were also located in the data center. And especially even around the areas where the crack unit supply air was discharged, there was also happened to be located near the floor mount PDU. So we saw a lot of density of cabling that existed underneath the floor, as well as generations of other interesting equipment that you find under any raised floor when you're doing an assessment. So yeah, pretty typical, I think, of a raised floor that evolves over time and ends up with sort of a derating of capacity in the systems because of all the infrastructure that's underneath the floor.
Okay. Now, what I've done here in this next slide is I've created a bit of an animation here. If you want to just walk us through this, this is from CoolSim 4. I imported this model. It was actually running CoolSim 3. I imported it to CoolSim 4 because it has a better graphics visual interface, and I made a recording of this. Maybe you could walk us through here a little bit, Todd, as we go.
Yeah, I'd be happy to. So I think the first thing of note, obviously, is as with many data centers, it didn't start as a data center, so it was office space at one point. It's not a perfect box. But primarily, the majority of the rack infrastructure, as you can see, is located kind of down that center aisle of the space. And you can see the 5 perimeter crack units that are located sort of scattered around the room. Again, it was something that evolved over time. So they weren't optimized from a layout perspective. They were just sort of added as capacity was required. In addition, you can see sort of from the front view that Paul's showing, there were some racks that had real significant density and some racks that had hardly any equipment at all. So there was really a diversity in rack loads that we saw, and that we'll talk about a little bit more from a strategy perspective. The last thing I'll note is in the back left-hand corner that you're seeing there, from what Paul's showing in red, is where the existing UPSs were located. So the UPSs were located in the actual data center white space, as well as some of the main switch gear, like the automatic transfer switch and some of the distribution that supported that infrastructure. So, there was certainly some white space in the data center that was being sacrificed to support that infrastructure. But again, it was pretty typical of an environment that evolved over time. Last thing I think that you'll note as Paul continues to animate it is that there's a shared center cold aisle for the majority of the equipment there, that one real long row.
Welcome to GoToWebinar, Web Events Made Easy.
To the topic of the webinar today, which is strategies for modernizing existing data centers.
Welcome to GoToWebinar, Web.
And today, what we really see modernization as from a design perspective is to take an existing data center environment.
It all running? Were all 5 of those units running?
Yeah, they were. And relative to ASHRAE standards, they had a relatively low inlet temperature, I think. But again, the reason that they were doing that from an operations perspective was because in a failure mode, they had too high of an escalation of supply inlet temperature. So they were trying to keep it at the lower end of that threshold, around like 68 degrees. So
Right.
you know, there was they were all on, they were all, you know, running, and it was really cold in the data center.
Yep.
Certainly a lot colder than it needed to be.
Yeah. You see here that the units aren't pulling much heat out. I mean, they're pulling 50 kW out each. That's a little over, 10 tons. They're, what are they, 30-ton cracks pulling 10 tons out a piece?
Right.
And the problem you run into there is, you're way under your design center, so the efficiency of the room is terrible. The coefficient of performance is going to be awful. The energy efficiency is awful. I suspect that if you did an energy measurement on this thing, then your energy consumed by the cooling unit may be equal to or greater than the energy being consumed by the IT equipment itself.
Oh, absolutely. Absolutely. I think you can make that assumption just based on this information here.
Now, I've got a bunch more runs here. I won't go through them all. Let's go ahead and talk about what their needs were and what you did to try to get them on the path to success.
Great. So, in addition to wanting to improve the existing conditions in the space, they also wanted to actually leverage that data center more as again, sort of a global center of operations. And as such, they were actually running out of UPS capacity. So the first goal of the data center effort was to actually increase UPS capacity and maintain an N+1 configuration on the UPS architecture. And in addition, they needed to gain back some white space in the data center. So because the existing UPS and switchgear took up so much sort of really valuable white space, they wanted to try to gain that back somehow, both through a virtualization effort, right, and some net rack space gain, as well as through freeing up some white space. Maybe most notably, they had, as I mentioned before, some pending virtualization projects that they really wanted to actually run the primary systems out of this data center that would result in loads of about 18 kW per rack. And with the existing environment, they were unable to support that type of density. So another goal was to be able to provide cooling capacity that would support that type of IT infrastructure and those type of virtualized loads. Obviously, they wanted to get back to that N+1 cooling configuration, both in the existing infrastructure that they had and anything that had to be added as a result of supporting the virtualized loads. And of course, with any data center, we needed to minimize the downtime to the space. So there's a lot going on, obviously, a lot of different infrastructures being touched, but really, I think this is a good frame of what the overall strategy and goals were for the project.
So design strategy here?
Yeah, so once we, after taking a look at the existing model from CoolSim, again, that gave us a great baseline to understand what was happening environmentally in the space. And in addition to that, we worked with the IT team to really understand what the load profile was in the existing racks, as well as what they projected to move and shift once the virtualization project was implemented. So there's equipment coming from a lot of different data centers globally, as well as virtualization efforts going on. So we wanted to just understand both existing conditions as well as what was going to happen dynamically with the IT load. So in regard to the strategy, in order to get white space back and increase UPS capacity, really the only, the best solution that we had was to actually create a separate room outside of the data center for the UPSs. One thing that allowed us to do was minimize downtime because we could build that system in parallel, meaning we could add the new UPSs and all the associated infrastructure, switchgear, et cetera, and we could also add overhead power distribution associated with that UPS system. That would be the new new power distribution infrastructure inside the space. So again, in order to help improve the performance of the crack units, we'd be removing all of that underfloor cabling, and we knew that we could do those efforts in parallel. The next piece, in order to support the highly virtualized loads and the 18 kW per rack projection, is we decided to take a zone approach. So we created a high-density zone in the space that we utilize in-row cooling and hot aisle containment. So we're really almost creating a self-sustained pod specific for the highly virtualized loads and high-density equipment that they expected in the data center. And when they looked at the growth in their IT environment, that's really where they saw it. So we needed some infrastructure to be able to grow improve their ability to support those types of loads.
Mm-hmm.
And in doing all of this, we wanted to obviously improve efficiency. So to support the in-row cooling, we actually implemented a new chilled water system, so new chillers and an N+1 configuration, and added Waterside Economizers to that because there was no free cooling utilized in the data center when we started the project. So we believe chilled water was a good decision and the right decision to support the type of high-density loads they were talking about, and also give us some great ability to utilize some free cooling.
So do I understand correctly that the existing cracks in the room, the downflows, were DX units, not chilled water units?
They were actually, I'm sorry, correct. They were DX units with condensers on the roof of the building.
Yep. So you went for chiller, kind of a long-term goal. In other words, buy the chiller and you'll be able to use it going forward. It's the right thing to do in terms of energy efficiency. Use Waterside Economizer and first pipe it to the pod, and then over time use it other places in the data center, I would think, right?
Yeah, exactly, Paul. So we obviously had the infrastructure to support the first pod, and then in addition, we actually pre-piped, right, some additional pods that, as we worked with the IT team, they said, well, we'll start retiring equipment here, which would free up sort of additional availability for these additional pods to be added. Mm-hmm. So what we did was sort of build some projections for where those pods would go, and built out that chilled water infrastructure so they could add the pods without downtime to the data center operations in the future.
Right. Yep. Makes sense. So here is the final design. Again, I did some crack failure analysis on this as well, just to show the differences. But first of all, let me see over here. This is the new pod area. So instead of having a UPS over here now, you've built a pod with 4, it looks like, cooling units in it, 4 in-rows in it, right?
Yeah, that's correct, Paul. So actually the UPS's, the new room is just south of that pod, right beside where you see the wall there. Mm-hmm. So it's very localized, which is great. And then we utilize that space to implement the new high-density pod, as you mentioned, and we utilized 4 24-inch wide chilled water in-row cooling units.
Mm-hmm. Now the rest of the room is relatively changed. You've still got gaps over here, and you've got the servers pointing the wrong way. That stuff's longer term, right?
Yeah, exactly. So as you looked at sort of the iterations for how the improvements will be made, first we created the pod. That's going to allow them to migrate some of the higher density loads from that legacy area or older infrastructure into the pod, as well as collapse some other equipment and consolidate from some of the other global sites. And then, once that's done and we sort of get back to the relative kind of new baseline, then they can take steps to start improving the existing space that wasn't touched as part of this. And one of those things was just to add a little bit of cold aisle containment for that existing infrastructure on the shared cold aisle, which I think is shown in this simulation.
Right. So to start that, you put curtains on the end caps, right? And I see
exactly.
Also here you've got some baffles along the in the center here. You've done some sealing there in the center between these.
Exactly. So there's certainly a lot of fire protection work that would have to be done in order to create a fully encapsulated cold aisle in this case. So in order to make a small incremental improvement, what the customer opted to do was just add some curtains on the ends as well as sort of in the gaps in the row. And they did sort of, even in the short term, see some incremental improvements in the space. Now, in addition to that, what we did from a management and a DCIM perspective was to give them a little bit more granular data. So when we started the project, they were just sort of measuring temperature, humidity at the room level. And what we did was added rack level sensors to give them, again, more granular data to really understand what's happening in the space.
It looks good. Let's take a look and see how we're doing. Again, I ran crack failure to see what would happen as we went round robin. My design here for crack failure goes in a clockwise direction, starting with this crack over here. This one tends to be the more sensitive one, so let's go there first. and take a look at how things may have improved. Now, you've still got racks pointing in the wrong direction here, so it's not going to be a panacea. And I think it's important for people to kind of know that it's not going to be a panacea right away.
Mm-hmm. Yeah, exactly. I mean, again, there's there's only so much you can undertake in one project, right? Especially especially one of this size, I think. And so, the customer looking at this data, they were able, again, and really the global real estate team, which oversees the critical data center operations, were really the sponsors of this project. So the data that you show here through CoolSim, we're able to sit down with all the project stakeholders in real estate, facilities, and IT and say, here are some areas in the data center that are really causing us some problems, and here's why we need to make some of those changes. So they could increase, sort of move that up in the priority list of the projects on IT.
Yes. So it looks like things have improved. We've still got, this is still the area that we're running into the problem with the racks being backwards. And that's not going to go away. Those are going to be problematic. One of the things I wanted to show here is if we take a look at the supply air, things are better than they were before because we've done some work to do cold aisle containment. So the cold air can no longer leak. It was leaking right here. You still see a little of it coming up now through the grills in the ceiling, but it can no longer leak right around these end caps.
But also through some of those gaps, some of the
gaps on the sides right here.
Yeah, a little bit on the side, a little bit too. Yeah.
It's being better managed than it was before. So now, have you? I would think here that the temperature in this room is going to be much lower than it was as well, much more improved. We take a look at the maps. We take a 6-foot slice here. See, we're seeing quite a nice contrast there in terms of the consistency. You can see, of course, where the racks are backwards right there. But the rest of that is a pretty uniform blue right down the center of it, and those baffles are helping to keep that situation pretty cool.
Yeah, absolutely. Again, it was a great first step for them. Again, so one, to create a separate zone on the high density side to be able to support that infrastructure, and then again take that incremental step with the curtains to create that new baseline, right, and understand where they work today. And as technology refresh happens, and as changes are made in the data center, to able to continue to start making more improvements to the use of that space.
So see right here, we can see there's no wrap around the ends. This is often what we see, right, Liz, is it wraps right around the end here.
Right, because the curtains went up to the ceiling, as I recall, on the ends, but not above the racks themselves. So there was that option for the air to circle around, but it did not.
Yep.
Right, and again, that was really a fire protection decision,
right, exactly,
or really a cost decision to not modify the fire protection.
And I was also modeling this as an N+1 configuration. Actually, I have 2 of them shut off in this simulation, and we're able to hold temperature in that pod with just 2 of these units on. So that's also very positive from a reliability point of view. I don't know if you've fully loaded there yet or not.
Well, it's not. You can see some of the equipment is not. The pink faces are active racks, and the gray faces.
The gray faces
for the most
are not.
part are inactive. Yeah. So
in my models,
still to be built out. Yeah.
Yep, exactly. So it was really those loads represented were all the equipment identified in the existing data center that was going to move, as well as some, sort of the phase 1 of the global consolidation that was going to move into that pod. So it certainly wasn't fully built out, but it was the first step in that project.
Now, just for those of you who haven't seen this kind of work before, in CoolSim, these animations are also built so you can see the air coming in and being distributed in the environment. So these are all the same simulation you get each time. These results come out. Very easy. You don't have to do anything. Just push a button and these things are generated. So I don't go through them all because there's quite a few, including slices that walk through the data center in this configuration. But I wanted to, in the interest of the webinar, to show you enough of it so that you got the idea of what was going on. Okay. So if you want to just go ahead and start to wrap it up, tell us sort of the summary. We'll open it up and start to take questions. It's about quarter of. We've got about 15 minutes for Q&A. Todd.
Great. Yeah, I'll keep the summary pretty brief. You know, again, from a goals perspective, one, we had to add capacity in the space, and that was really important. So we're able to add UPS capacity and also gain back some of that white space. So we created the pod to support high-density loads, and in doing so, we were able to create an N+1 configuration in that pod and gain back that redundancy to the existing crack unit. So that was a great win, I think, for the project. That also improved efficiency. We wanted to be able to extend the life cycle of the crack units, obviously, and I think that we were able to do that just by better utilizing them and adding some of the containment that we did. And again, agility was a big word. It's something that we think is important in designs, and by adding power distribution overhead, by giving them a zoned approach, they have a little bit more agility in that space to be able to support refreshes, dynamic changes in their IT environment, and you know, more consolidation inside the space. And you know, lastly, just adding a little bit more granularity as far as what they had environmental visibility into, improving the DCIM infrastructure that they had was really important, and we think that allows them to better proactively manage the space from an infrastructure perspective as well.
Just out of curiosity, Todd, how did you handle how did you get them to buy into the idea of a chiller? Chiller's a pretty expensive piece of equipment. These guys were using DX units. Those are cheap. That's why people like them. But you know, the issue of putting a pod in, adding chilled water, what was your line of reasoning there, and what did the numbers feel like?
Yeah, so there were a couple things at play there. First, you know, efficiency was certainly a component of it, and they did want the ability to do free cooling. There was not availability from a space perspective to do any type of air side economization. So we really looked at water side economizers as a result. And then in addition to that, the rooftop space was really limited. And so when we looked at the scale, you know, sort of the scalability of the space and the ability to add to it, we thought that the best decision was to add the redundancy from a chilled water perspective. Yep. We also felt like that was the best mechanism to support high-density loads. So as those loads grow, we really felt like chilled water was the right architecture. And again, by sizing the chillers to support growth, we felt that it enabled them to a little bit more efficiently support their growth without downtime going forward. So there was a bigger price tag. I think that, you know, we looked at about 120-ton chillers, and there were two of them just to sort of support this infrastructure. Mm-hmm. And so, you know, you're talking about a $500,000 to $600,000 investment just on the equipment side, you know, right, without the labor. So it was an investment, but I think the customer saw the long-term benefits of it, and it was worthwhile on the project.
Yes. Okay, so sometimes the issue is that they don't have a lot of choice with respect to even DX units. I mean, the DX units are cheap, but they're not scalable. You need room in a to put the condenser. You need to pipe it out to the condenser, and you need 2 pipes for every one of those things times N units. It starts to add up, doesn't it?
Yeah, it does, absolutely. And you know, in this case, again, this is a multi-tenant facility. Multi-tenant building from a office space perspective, right? So obviously, our customer occupied a majority of the building, but you had 6 floors, and that's a long way to run, you know, piping in any case. And so we really only want to do that once. And so again, chilled water really became, we think, you know, in our mind, the right decision from a load perspective, or excuse me, from the ability to support high density loads, but also from a long-term investment TCO perspective. We thought, you know, let's put that infrastructure in once, and then give them the ability to just dynamically add to it in the future from, you know, inside the white space.
Yep. Okay. So now what I'd like to do is just open it up for questions. The easiest way for us to do questions is for you to just type them in on the chat window, and we'll pick it up and run back and forth with that. I'm going to hand this back over to Jen and let her sort of handle questions. Do we have any questions for any of the 3 of us at this point, Jen?
Yeah, We do. We do have a couple questions. The first one is, why do cooling units fail? Is it the failure frequency of fans, cooling fans, controls, water leaks, etc.?
Yeah, well, I would say all of the above. You know, they do fail. There's two issues that go on, and what in a design of a data center, the reason you want to do crack failure analysis is really twofold. Number one, you got to maintain the units, and to maintain them, you've got to shut them off so that you can change filters and change valves and change things, just normal maintenance, belts. So they have to go down periodically for just routine maintenance. Second of all, if you want to build an N+1 design and one fails, for example, a compressor fails, this is not uncommon, belt fails. Now, a lot of them are direct drive these days, so they don't have belts, but in the old days, belts would fail a lot, compressors fail, condensers, things leak, fans fail. In that case, you want to make sure that you've got enough cooling capacity to be able to handle the situation. That's the easy part. The harder part is getting the cold air over to where you want it to be so you can cool the unit, the IT equipment that's hot. So the point is that oftentimes you have enough cooling capacity on paper, but what you don't know until you run an analysis like this, like we've done with CoolSim, can the cool air get to where it needs to go under the condition where these are on and these are off, that kind of thing. So that's why having studies where you can turn them on and off and run them concurrently to understand the dynamics under the failure modes is an important component of overall data center design.
Yeah, I would agree with that, Paul. And just to briefly add to it, you know, there are a lot of moving parts to cooling units. So any part can fail, and that would cause a failure in the unit. And I think, you know, at our organization, you know, from an assessment perspective, we're asked a lot to look at an existing environment just like this, where the customer will say, we know on paper we have double, triple the cooling capacity that we need based on the IT load, but when we lose a cooling unit, we lose the room, right? And that's why utilizing a tool like this and having the ability to do it on this project was just a great way to be able to articulate to the customer exactly what was happening.
Yes. Okay, Jen?
Sure. Next one is, can you clarify what changes were made between trial 0 and trial 1, those runs?
Sure. In each of the trials, I just simply turned off a cooling unit out of the 5. So trial 0 had them all on, which is how Todd entered the room. You know, when he first got there, they were all running because they keep them all running. The idea about N+1 is that if any single unit fails, the other 4 in this case should be sufficient to satisfy the needs of the room. So all I did was turn off the first unit, and then in trial number 2, turned off the second unit, turned the first unit back on, etc. I went around the room in a round-robin kind of fashion, turning off a successive unit and then making another concurrent run. In CoolSim, you can submit those all at once, and they come back all at once, and you can look at your results all at once in a PowerPoint form like we are here to understand the implications of airflow under those various conditions. So between 0 and 1, in 0 I had them all on, and in trial 1 I had one of them off, signifying the N+1 state, or the state in which 4 were running and 1 was off. Okay?
All right, for such existing conditions for this data center, maybe just adding 1 or 2 extra crack DX units will be more cost-effective versus such a big investment. Can you tell us what the ROI for this project is?
Yeah, great question. I think the answer has multiple layers. So first, definitely just adding a couple crack units would have been a smaller investment for the end user, although they were running out of white space. And so in this case, they needed to increase the capacity on the UPS side, right, to support more equipment in the data center. So that was an investment they were willing to make. However, if you look at the chilled water, for an example, they also paid extra to add economization in this case. And so based on the bin data for the location and based on the kilowatt hour rate that they pay for power, you know, they saw about a 5-year, expect about a 5-year ROI on the addition of the Waterside economizers for the chillers. And the modernization effort that we went through was expected to be about a 10-year life cycle at minimum for the data center. So I felt that that investment was worthwhile. So there was certainly an ROI component, and there was a reliability component, I think, as well. And improving the reliability of the space was really critical because they had lost that redundancy in the crack unit. So again, I think there were sort of multiple levels to the strategy for their investment. But overall, I think it definitely was the right one.
I think it's a fair question in the sense that sometimes, Todd, I find that it's difficult to convince people to take the long-term view, and what they want to do is just use DX units because they're cheap and quick, right? We've seen that before, right, Liz?
Yes.
Yeah, I totally agree, and it's tough to look, tough to look long-term, Paul, like you mentioned, and I think that what we do find, though, is that customers come to the sort of end of the useful life, or they come to a fixed capacity in the data center. For example, they start running out of UPS capacity, and when they're at that point, they know they need to make an investment. The smart thing to do, in our opinion, is to think about that long-term strategy at that point, as opposed to just sort of doing a one-to-one replacement. So a lot of the work that we do is just to help our customers sort of develop that strategy for how they can extend the life cycle of their spaces.
Right. All right, Jen, what do you got now?
All right. Should we consider higher airflow rates and higher temperatures? And then the next question is, what is the actual temperature inside the computers where damage could occur?
Yeah, well,
it depends on how old the equipment is. Yeah.
It depends, doesn't it, Liz?
Yeah.
I think in general we should consider higher. Well, airflow rates. The funny part is, as the delta T's rise, the airflow rate declines. I mean, another way to say that is, the airflow rates aren't going up that high yet. The delta T's are growing on these servers, and now you see the TC99 ASHRAE recommendations for even higher rack inlets than we've been running traditionally. So I think to answer the question, yes, we are seeing higher temps, and we should consider higher temps. Remember, the airflow is related to the delta T's and the thermal loads. Assuming a 20-degree delta T, the airflow required is about 156 CFM per kW in order to dissipate that heat. So that's generally what we use as a delta T of 20. Now, servers are getting to the point where they're 30, so that flow rate is going to decline. But I think that 20 is conservative. I think it gives you a good feel for what's going on in the room. If you can pass the tests at 20, it'll certainly pass it for 30. And furthermore, the issue, Liz, I think we see more than anything is too much supply air, and not so much about the server, but just too much supply air.
Right.
The high supply air on the crack units, again, makes the delta T's across the cracks low, and when you do that, it makes them less efficient because they're designed for a certain design center, and you're not there, so they're more inefficient, they consume more energy, and the whole thing just works.
Yeah, and even assuming, allowing for, an increase in the temperature rise across the equipment, still doesn't have, what really matters is how much air gets to the front, to the front side of those racks in the first place. And so managing the airflow and getting it to go where you want it and preventing the wrong air from getting to those rack intakes is really the most critical thing. What happens inside the equipment, if the air, gets hotter. Now, the problem with the air getting hotter is, of course, when that exhaust air does get re-entrained into the rack inlet. So now you've got hotter air coming in than you may have had in the past when there was only a 20-degree delta T. That air, if it mixes with the supply air, it's not going to be, we're going to have a warmer mixture of air coming into the rack inlets. And so the larger the delta T on the rack, if you still have that problem, the more harmful it can be. So
that's correct.
It's a very complicated kind of, set of, there are a lot of factors involved.
There are a lot of factors. So, and we, Liz and I are familiar with the IceTac product, which we were responsible for, of course, at Fluent Corporation, and that is specifically designed to model the interior of the IT equipment and model the thermal situation in there. So we don't really know, without having those models, exactly what goes on inside that package, but I can assure you that the people who designed it do.
Oh, yes.
Because they're using IcePack to model that behavior. So I guess the long and short of it is that we do design still to, and we recommend still, the ASHRAE 80.6 Fahrenheit max intake temperature, because if you can get it there, then you're fine. If you can convince your operational people to run higher than that, good. But Todd, I think you'll agree, we've struggled to get people up to 70 degrees from 55 degrees in these data centers, right?
Oh, yeah, absolutely. I mean, I think going to 80 point, I mean, certainly you see some progressive organizations in the industry pushing the upper end of that envelope that's listed in TC 9.9. But I agree, you know, a lot of organizations aren't comfortable getting there yet. And, you know, for some, too, we see a trade-off in that if you increase to a certain point in the supply inlet temperature, then you also see an increase in fan speed across the server. So sometimes there's an efficiency trade-off between what you gain by increasing the supply unit temperature versus what you lose by increased fan.
You are correct, and those are generally assumed to be about 77 degrees, by the way. And I've seen studies show that beyond 77 degrees, it's a point of diminishing returns. So, you know, keeping the rack inlets at 80 or below seems to be a good general rule of thumb, is what we find.
Agreed.
Okay, Jen?
All right. Do crack units come with DX coils and chilled water coils? If so, would this not give you 100% redundancy?
Not all cracks come that way, I guess, is the answer.
Yeah, I mean, you know, in this case, that wasn't how the crack units were configured. That is an option that we see organizations take, is to utilize that that style of crack unit. So I don't think that you know, you can still have a failure of the component inside the actual crack unit, even though you may have two heat rejection mechanisms sort of on the back end. So I do think it's design dependent. It does give you an increase, I think, in redundancy over just a 1-to-1 ratio of crack to condenser, but it doesn't automatically give you N+1 redundancy in my mind from a design standpoint.
Okay.
All right. How much cooling capacity is needed per rack or CPU?
Well, again, I did touch on that. We generally assume 156 cubic feet per minute per kilowatt of power, and that falls right out of the heat transfer equation, which is heat transfer for a device, convective device, is equal to the density times the mass flow rate times the delta T. So mass flow rate, if you assume the density is constant because you're not moving the servers up and down in the atmosphere, then mass flow rate and delta T become the two primary factors. They become the two factors that drive the heat. And if the heat's a kilowatt, then the delta T is 20 degrees, then it drops out that the CFM is about 156. And that's how we do it. That's a general relationship. It does change a little bit when you are in Denver, I suppose, because your density is a little different. But generally speaking, that's how it's done, and that's what we use in the system to generate the heat loads. Now, if you do know the heat loads, it's better, of course, because then you can calculate them. And over time, I'm sure, because we're beginning to get this data, we're going to be able to see what the CFM of the services are by sampling data in, measurements in the data center. But we don't have all of those yet, and right now the data is coming back as RPM. And you have to now take RPM, find out the fan, find out the flow rate, assume the delta P is a certain amount, and then, so 156 per kW is a really fairly good unit of assumption. Don't you think, Liz?
Yeah, I do. Well, for 20 degrees, yeah.
Yeah. Okay.
All right, so each cabinet power strip was disconnected from underfloor outlets one by one and reconnected to outlets provided from above?
Yeah, great question. So the first effort that was undertaken was just a verification that each server had two feeds, an A and B feed, and dual power supplies as a result. So that was the first effort that the customer undertook, was just to have that verification. And then redundant, A and B as we would call it, busways were run overhead. And in order to make the cutover live, what we did was sort of disconnect the entire B side on one rack and plug it in, and then move the A side over. So that transition work was done live and was able to be done successfully, just with obviously a lot of great coordination between the contractors and the owner.
Nice job.
Mm-hmm.
Okay.
Right. What DCIM approach or tool was used, and how well did it fit into the company's various departments?
Great question. So this organization happens to have a homegrown DCIM application, and there are a variety of reasons. One of which is they have some great in-house expertise to be able to develop that type of software. But I think really from a strategy perspective, what they had was a very sort of high-level view of the data. So, for example, they could see, through by dialing in just to the crack units, they could see, what the supplier temperature was, or what the return air temperature was, et cetera. They could see loads on the UPS. They could not get into even though they had metered PDUs, they couldn't quite get into the load per PDU. So again, what we did was just identify some components that were going to improve the level of detail that they had inside that interface, and then enable it just through the control wiring and the sensors required as part of the project. So it was homegrown, I guess, at the end of the day, but I think that you could have taken sort of anyone's sensors as long as they had the right sort of communication protocol and tied them back into the system that the customer had.
All right. Was the data center brought down at any time during the project while adding new UPS modules, chillers, et cetera?
Yes, great question. And there was one scheduled downtime that occurred, and that was because we had to add new feeds from the building emergency distribution panel and normal power, normal distribution panel to provide the infrastructure for the new equipment. So there was one coordinated downtime that was done for the project. It was scheduled, about 6 months in advance. But again, in a great effort by the contractor and certainly the owner, they were able to maintain that date, and the cutover was done at that time.
All right. You mentioned overhead power distribution. Is there a benefit other than removing underfloor clutter?
Yeah, well, we think there are benefits. Certainly the clutter, as you said, in our opinion, and I think as you can see in the models, do impact the capacity and the performance of the crack units. And in addition, we think that it gives more flexibility. So in the existing power distribution infrastructure they had a PDU that was, a power distribution unit with a bunch of breakers in it, right, that sat sort of on the perimeter of the room, and then they had to run a couple whips under floor to get to every rack. So if they needed to make any changes, they had to go back to the PDU. In order to do that, run the whip under floor and create it new just for that project. With overhead distribution, in this case they used a busway system, they have a little bit more agility in that if they are changing, say, the PDUs that go in a rack or adding new equipment that requires some change in power feeds, they can just change the bus plugs overhead, again, without downtime to the system. And we think that gave them a lot more flexibility to support the sort of dynamic IT changes going forward.
All right. How long did it take for the CoolSim application to be loaded up with all the required data?
I guess that would be a question for me.
Yeah, Liz, that you built these models.
It's not that it took long. I think the thing that always takes long doing a project like this is getting answers to questions about this piece of equipment or that, or there's some aspect of a rack, heat load that it's vague, or because the customer oftentimes doesn't have the information, and so there's a lot, that I think is the one thing that takes up time that you don't really anticipate, having the question, posing it to Todd, having Todd have to go back to the client, find out the answer, and the back and forth. So that's, a piece of it. But in terms of the setup time, it took probably no more than maybe, I don't know if it was 4 hours, I'm guessing 4 to 6 to 8 hours maybe to set up the whole thing, maybe less. I'd have to look back in my notes, but it depends upon, when you set up a model like this, if you have a row of of racks and they're all the same, you can set that up as one object, and it takes seconds to do, a minute say, to set it up. But oftentimes when you do a model with a fair amount of detail, then you want to set up the racks individually, and we did that in this case here. So some of the racks have different heights, so they have different heat loads.
Well, also we used a rack builder in this one. Yeah.
So it's all that granularity that really it takes up extra time. So you could build a model like this fairly quickly, within an hour with very little detail. But if you want to put that level of detail, and then it pays to take the time in the beginning and be careful about it.
Let me make the point here too, Liz, that oftentimes making them coarse at first is good because it gives you the feel. You and I have found this a lot. Lay them out. If you're going to use a modeler like this, don't be afraid to lay them out with, at first, a coarse level of granularity. You're still going to learn a lot. I know there's debate about this, and our competitors love to point out that they can put more detail in at certain points. But the point is that if you have an overview of what's going on in the room, even big parameters like how much air is coming into the room versus how much is being used by the servers, it will tell you huge amounts of information about what's going on in your room and what you need to do.
Right, and you can always set up a model take a coarse, model like that where you don't have a lot of detail, and you can run it, and while it's running, you can continue on with the setup. Give it a new name, version 2, and now you can put in a lot more detail, and you can sort of run one that's simpler, simplified, and then add while you're adding the detail to the next one. So.
Yeah, Liz, it's the old thing. I think Einstein said all models should be as simple as possible and not simpler. In other words, try to get it as simple as you possibly can to capture the physics of what you're trying to prove or disprove in the room, and stop. It's not a CAD system. Don't put coffee cups on the table. We've seen this, haven't we, Liz? We've seen, we've seen tables in the room and coffee cups, and you don't need that level of detail. Even server level detail isn't going to give you much more if, for example, you don't know what's going to be in the room.
So, but if everything is blanked too, I think the time that you want to use server level detail is like the time what Todd showed here, when there are large gaps or even small gaps in the racks where air can leak by. That's really the most important time that you want to use that model.
Okay. Jen, we're closing in on the hour, so a couple more?
Yeah, a couple more. What is the advantage of putting strip curtains at the end of the rows, perpendicular to the length of the racks, versus putting them on top of the racks, parallel to the length of the racks?
Well, I think preferably would like them both, but I think logistically, Todd, in your case, it was not feasible to put them up on top, and it probably was on the ends, right? I mean, the quickest way to do it was probably the ends.
Yeah, exactly. It was really just sort of what was the easiest solution to implement inside the existing environment. And again, if we were to do both, then we would have had to make augmentations to the fire protection infrastructure, and that wasn't a step the customer was willing to take yet. So that's why we chose to put them at the end of the rows, which I think, as Liz pointed out at one point in the presentation, just helped prevent a lot of that recirculation of air into the cold aisle.
All right, and then could you describe the type of waterside economization you used in more detail? Did you use an evaporative cooler or a dry cooler or something else?
Yep, so it actually, the chillers were actually packaged chillers that included Waterside Economizer modules. So it was actually built and configured at the factory. So it was not an evaporative cooling system. It was actually a component to the chiller system itself.
All right, and then lastly, everyone usually asks if they can get a copy of the presentation, and we will have the webinar. We've recorded it, so we will have this available to you in the next couple of days. And for those that have chatted with me, through either the chat panel or through the question panel, we'll make sure that we email you the link to view the recording. So we've made note of that. And on behalf of Paul and Liz and Todd and myself, I thank you for joining us today online, and we look forward to sharing another great case study with you and hope you can join us again. Have a great day, everyone. Thank you.
Thanks,
Jennifer. Thanks, Todd. Have a good day.
Thank you.